Lesson 4, Mechanics Connected Particles. When two objects are connected by a string and the string is held taut, there will be a tension force in the string. We can model the objects as particles and we model the string as light and inextensible. If the string is inextensible, then the tension will remain constant throughout the string. By Newton's third law of motion, the forces acting on the particles will have the same magnitude but will act in opposite directions. So to illustrate what we mean by this, imagine we have a particle A connected via a piece of string to a particle B, and the string is held taut. There will be a tension force acting on particle A, like this, and there will be an equal and opposite tension force acting on particle B. Objects can also be connected by what we call a rigid rod. For example, a tow bar connecting a caravan to a car. Similarly, there will be forces acting on the rod, but unlike a string, a rod can be under tension or compression, which is also called thrust, and you might be asked to identify which. So, for instance, we might have a particle A attached to a particle B, connected to a particle B via a rod, and if we look at the forces in the tow bar rather than the forces on the particle, then we may have the situation where the tow bar is being pulled like this, in which case it is in tension, or we may have a situation like this. Here are particles, here is the rigid rod connecting them, where the forces in the tow bar look like this, in which case it's in compression. So these blue forces are forces in the tow bar, acting on the tow bar. They're not the forces acting on the particles. If this sounds a little bit unclear, this will become more apparent as we do some examples. Let's look at example 1. We have two particles, so here is our modelling coming into play. A and B, which have masses 3 kilograms and 4 kilograms respectively. They are connected by a light, inextensible string. The particles are at rest on a smooth horizontal surface. A force of magnitude 7 newtons is applied to particle B in the direction AB, and we have to do two calculations based on this. The first thing that you must do is draw a force diagram. You cannot solve these mechanics problems without a clear force diagram in place. So we have some kind of surface. On our surface we have two particles. Let's call this one particle A and this one particle B, and they are connected by a light inextensible string. Let's draw on the forces. So both particles will have a weight. Particle A will have a weight of 3g, particle B will have a weight of 4g. Both particles will experience a normal reaction force, which is balanced by the weight. There is no vertical motion here. So RA and RB, they're different. Now, forces acting on the particles. There will be a tension force here, pulling particle A forwards like that. And by Newton's third law, there will be an equal and opposite force like this here, pulling B backwards. So B sort of pulls A forwards, A pulls B backwards. Now there is one final force, which is the one of magnitude 7 newtons applied to B in the direction AB. So the direction AB is left to right, which means that there is a 7 Newton force acting on B like that. Now, we do need to be really clear. The 7 Newton force only acts on B. It is the 7 Newton force that creates the forwards motion that results in the string becoming taut and creates the tension in the string that pulls A forwards. So this 7 Newton force only acts directly on B, not on A. As a result of this 7 Newton force, a tension is generated in the string and this tension acts on A, but the 7 Newton force is directly applied to particle B only, and that's really important. So we're going to aim to solve the problem and calculate the tension and the acceleration, and there are 2 methods that we can use to do this. In the first method, we treat the whole system as a single particle. So we imagine that rather than 2 separate particles of 3 kilograms and 4 kilograms, we have one single block of a particle which has a mass of 7 kilograms, so a weight of 7g overall. So this is A and B combined. There'll be a single normal reaction force upwards like that, and there will be a forwards force of 7 newtons like this. Now, because we've combined the 2 particles, essentially the 2 t's, one going left to right and one going right to left, cancel each other out, and we're no longer concerned about those forces at the minute. The system is accelerating to the right in the direction of the resultant force, so we'll mark on the acceleration like that, and of course going to the right is going to be our positive direction. So Newton's second law of motion, F equals ma. We have 7 newtons, a resultant force to the right, which equals the mass of 7 multiplied by the acceleration a, and this very simply gives us a equals 1 metre per second squared. So that answers one of the questions, but it doesn't answer the second question of what is the tension in the string. So to do that, we would then have to focus on one of the particles, either of them. I'm going to focus on particle A. And again, I'm going to choose going to the right as positive. Now, if we look at the forces acting on A, the only force acting horizontally and directly on A is T. Remember, the 7 Newton force acts on B directly, not on A. So the resultant force is T going to the right, which equals the mass of A, which is 3, multiplied by its acceleration 1, which gives us a tension force of 3 newtons. And this is one way of solving the problem. Now, the second method that we can use to solve a connected particles problem is to consider each particle separately and apply Newton's second law of motion, F equals ma, to each particle individually. So we're going to start off by looking at the forces on particle A. Remember, we're going to the right as positive. So the force acting on A, the only horizontal force acting on A is T. So we have T equals m, which is 3, multiplied by the acceleration, which is A. So we have an equation here, 2 unknowns, T and A. Now, let's look at the forces acting on particle B. Remember, going to the right is the positive direction. So we have 7 newtons. We then take away T, because that's going in the opposite direction, which equals the mass 4 multiplied by the acceleration A. So our resultant force is 7, take away T, going to the right. We have a pair of simultaneous equations. And these are a particularly easy pair of simultaneous equations to solve because one contains a positive T term, one contains a negative T term. So if we add them together, we will cancel out T. So this gives us 7 equals 7a, so a equals 1 metre per second squared, and then if we substitute back into either equation, I'll substitute into equation 1, this gives me T equals 3 newtons again. I quite like this method because it gives you all of the information in one set of equations. You can then solve them and find both your unknowns together. Example 2, let's read through this really carefully, highlight any modelling words, and then draw a clear force diagram. So we have a car of mass 1,000 kilograms, which is towing a caravan of mass 750 kilograms along a horizontal road. The engine of the car exerts a forward force of 2,500 newtons. The resistances to motion are directly proportional to the masses of the car and caravan with the same constant of proportionality. The car accelerates at a rate of 1 metre per second squared. Find the tension in the tow bar. So there's a lot to break down here, but the first thing that's clear is we need a diagram that illustrates this information. So here's our road, which we know is not smooth. There's resistances acting on it. I'm going to have my car modelled as a particle here, and my caravan modelled as another particle over here. Now the car has got a mass of 1,000 kilograms, so 1,000 G, like that, and there'll be a reaction force balancing that vertically upwards. The caravan has a weight of 700 G and a reaction force like so. Now, the items are joined by a tow bar. So that is being modelled as a rigid rod, not as a light and extensible string. And the engine of the car exerts a forward force of 2,500 newtons. So let's draw on the forward force of the car, 2,500 newtons. Remember, this acts on the car directly, not on the caravan. So when we're resolving forces and using F equals ma later on, we need to remember that this 2,500 newtons is acting on the car. What this does is it results in a forward force that pulls the caravan forwards, so a tension force like this, which is counterbalanced by a tension acting on the car like this, but the 2,500 newtons does not act on the caravan directly. Now, the last thing we need to make sure we include is this information about resistances to motion, which are directly proportional to the masses of the car and the caravan. So what we're saying is resistance is directly proportional to mass in this question, which means that resistance is equal to K multiplied by mass, where K is some sort of constant of proportionality, which happens to be the same for both the car and the caravan. So the car will experience a resistance of 1,000 K, K times the mass, 1,000, and the caravan will experience a resistance of 750 K. It's mass multiplied by K. Remember, resistance opposes the direction of motion, or the intended direction of motion. The engine force of the car, which is 2,500 newtons, the green force is trying to pull it forwards, trying to accelerate it in this direction, which means the resistances will be in the opposing direction, as you can see on the diagram. So we have our very clear force diagram with all of the forces marked on it. In fact, we actually know the acceleration is 1 metre per second squared, so we can mark that information on too. So here we have the force diagram again, and we're going to solve this problem using the second method, where we consider each particle separately rather than treating the system as a whole. So remember, this one is the caravan and this one is the car. We're going to look at the forces acting on the caravan first of all, and I'm going to use F equals ma, resultant force equals mass times acceleration, and I'm going to treat any forces to the right as positive. So acting on the caravan, we have T in the positive direction. Take away 750k, which equals the mass 750 multiplied by the acceleration, which is 1. And we have one equation. Let's now look at the forces acting on the car. We've got 2,500 going in the positive direction, T in the negative direction, 1,000k in the negative direction, and this equals the mass of the car, which is 1,000 kilograms multiplied by the acceleration of 1. and we have a second equation. So our simultaneous equations, again, notice the fact that you have a positive t and a negative t, so adding these two equations together will easily cancel out t. So this then gives us, when we add them together, (2,500) minus 1,750k equals 1,750. So from here, we can calculate the value of k. And k equals 3/7. Remember, this is just a constant of proportionality. We can then substitute back into either equation. I'm going to substitute back into equation 1. So t equals 750 plus 750 multiplied by 3/7, which gives me, for my value of t, and this gives us a value of t of 7,500 over 7 newtons in exact form. So let's now look at a more complex problem. We have a train consisting of a locomotive of mass 50 tonnes. So first of all, make sure you understand how to convert that into standard units. That is 50,000 kilograms, and two trucks each of mass 10 tonnes. So that is a mass of 10,000 kilograms. The resistance to motion of the engine is 600 newtons, and that to each truck is 200 newtons. The driving force produced by the engine is 36,000 newtons. All the couplings are light, rigid, and horizontal. So we're going to carry out a series of calculations here. We will split this up into several stages, but the first thing we must do is draw a clear force diagram to represent this information. So we're going to start off by drawing a clear force diagram. So here is our horizontal road, and let's draw this system of connected particles. So we start off with the locomotive to begin with. We'll call that L. We then have a truck here, which we're not going to label as T because that will be confusing. We'll call that truck A. And then we have another truck here, which is truck B. So masses of these particles. The locomotive has a mass of 50 tonnes, so a weight of 50,000 G, and the trucks have weights of 10,000 G. They've all got reaction forces, like so. And let's connect them up with these couplings, which are light, rigid, and horizontal. Now, the forward force produced by the engine is 36,000 newtons, so we should have a force in this direction, 36,000 newtons. And we're then going to need to draw in some tension forces. So there'll be a tension here, which I'll call T1, counterbalanced by a tension here, Newton's third law, equal and opposite reaction forces. But because the coupling between A and B is a different rod to the coupling between A and L, that means that the tensions here are different. So we must label them differently, T2 and T2. You've got different rods, different tensions. Now, let's draw on the resistances to motion. So resistance to motion here is 600 newtons. So by engine, they mean the same as locomotive in the question here. And the resistances to motion of the trucks are 200 newtons each. So we'll draw these on as well. And the system is going to accelerate in the direction of the engine forward force. So we're going to choose going to the right as our positive direction. We're going to apply Newton's second law of motion, resultant force equals mass multiplied by acceleration. And we're going to look at the forces on L, the locomotive, the forces on truck A, and the forces on truck B separately. So if we look at the forces acting on L, first of all, we have in the positive direction 36,000, take away T1, take away 600, and that equals its mass of 50,000 multiplied by the acceleration of A. Let's now look at the forces acting on A. Now, going towards the right in the positive direction, we have T1, but we then have to take away T2 and take away 200, and this equals its mass of 10,000 multiplied by its acceleration of A. And then forces acting on B, in the forwards direction, we have T2. In the opposite direction, we have 200, and this equals the mass of 10,000 multiplied by our unknown value of A. And notice we have a system of 3 simultaneous equations. Now, interestingly, in this system, you will notice we have a minus T1 and a positive T1, and we have a minus T2 and a positive T2. So really, the key to solving this is to add all 3 of these simultaneous equations together to do the calculation, as we will eliminate T1 and T2 from our calculations if we do this. So we're going to do equation 1, add equation 2, add equation 3 to see what happens. Now, this gives us 35,000 equals 70,000 multiplied by A, which allows us to calculate A, which is 0.5 meters per second squared. So the acceleration of the whole system is 0.5. We then need to calculate the coupling, the force of the coupling between the 2 trucks. So that is, of course, T2. So we're going to simply substitute the acceleration into equation 3, which is the easiest one to work with, as it only has T2 and A as unknowns. So T2 is then equal to 200 plus 10,000 multiplied by our value of A, 0.5, which gives us a value of T2 of 5,200 newtons. And we've solved the first 2 parts of this problem. So the next part of this question tells us that the driving force is removed and brakes are applied, which adds a further resistance of 12,000 newtons to the total of resistance forces. Find the new acceleration of the train. So I've sketched the diagram again. I've left out the vertical forces because we know they aren't contributing to the forwards motion of this particle. There's no vertical motion. I'm not really concerned about the weight and the normal reaction. So just for the moment, I'm going to ignore them in this part of the question. Now you can see that the forwards force, the driving force of 36,000 newtons has been removed, but we now need to make sure we include an overall resistance force of 12,000 newtons. Now, there's a good opportunity here to actually use the original method that we looked at, which was to treat the system as one large particle. So treat the system as the whole rather than using F equals ma separately on each particle. Now, why might I do that? Well, I'm only interested in calculating the acceleration, not the tension between the couplings. So by treating the system as a whole, I simplify everything and I don't have to create so many simultaneous equations, which makes my working a little bit easier. So if I treat the system as a whole, I then have effectively one large particle, which is A, B and L combined together. The forces acting on it, well, we have effectively a huge resistance force, which is comprised of the 200, the 600, and the 12,000 together, which gives me an overall resistance of 13,000 newtons. We have no forwards forces acting. The individual tensions would cancel each other out when you combine all 3 particles together. So let's use F equals ma. Resultant force equals mass multiplied by acceleration. I'll choose going to the right as positive. So that means I have negative 13,000 equals the mass of the system, which if you add together all the masses of the individual components is 70,000 kilograms multiplied by the acceleration. This then gives me an acceleration of minus 0.18571, etc., minus 0.186 meters per second squared to 3 significant figures. Now, of course, this makes perfect sense because what we have is a deceleration. You've removed the driving force, so there's nothing pulling the system forwards, and you're applying the brakes, which of course will result in a deceleration. Now, let's look at the very last part of the question. We're still dealing with the situation where the driving force has been removed and brakes are applied, which adds a further resistance of 12,000 newtons to the total of the resistance forces. So we now have to calculate the new force in the coupling between the trucks, i.e. find T2, if the brakes are applied to the engine or to the end truck, and in each case state whether the force is a tension or a thrust. Now, this is really interesting. We weren't told in the information that we were given whether the 12,000 newtons was applied to a particular part of the system, which is why it made perfect sense in part 3 that we treated the system as a whole. Now here, we've got to now look at things separately. So let's start with part A, where the brakes are applied to the engine. So I'm now going to look at this locomotive on its own in a little bit more detail, and let's draw on the forces acting on the locomotive. So we'll just zone in on this locomotive. So there's going to be a tension force T1 in the tow bar, like that, and there is a individual resistance of 600 newtons, but then we know the braking force is applied to the engine, which means that's 12,000 newtons as well, like that. Let's draw on the acceleration of the system. We'll take going right as positive, and of course we're applying Newton's second law of motion, F equals ma. So this tells me I've got minus 600 minus 12,000 minus T1, because they're all going in the negative direction, which equals the mass of this object, which is 50,000, multiplied by the acceleration. And I have a single equation with two unknowns. Let's now look at truck A, or particle A, in isolation. It has a force of T1 in that direction, it has a force of T2 in this direction, and it has 200 newtons resistance like that. Again, applying F equals ma, we have T1 take away T2 take away 200 equals the mass, which is 10,000, multiplied by the acceleration. And finally, let's look at the last particle, the last truck, B. Forces acting on it, we have T2 in this direction, and we have 200 in this direction. So we're going back to this diagram up here to help us. So F equals ma, T2 is positive, 200 is negative, combining those two together equals the mass, 10,000, multiplied by the acceleration. So we have a system of three simultaneous equations. Let's add these three equations together and see what happens. Now, hopefully you will have noticed, as we've seen previously, we have a minus T1, a positive T1, a minus T2, a positive T2, so the individual tensions will all cancel out. Now, the addition then gives us minus 13,000 equals 70,000 A, and then A equals negative 0.18571, which, interestingly, is the value that we got for the acceleration in part 3. We now need to calculate the value of T2, so the force in the coupling between the trucks. So we're going to substitute into the third equation. So let's just make these clear with their labelling. Now, this interestingly gives us a value of negative 1657.142 ... Now, we need to interpret what's going on here. Let's look at particle B again. Now, originally in the diagram, the forces that we had acting on it were T2, which looked like that, and 200, which looked like that. And if you remember, we had said going to the right was positive. Now, the fact that there is a negative sign here tells us that actually the forces on B really look like this, which means there's particle B, or truck B, there's the 200, which was in the correct position, but T2 is negative, so T2 acting on B should actually have looked like that. Now, remember that B was connected to A like this with a tow bar. So here's the tow bar connected as a rigid rod. So this means that T2 acting on B looks like this, T2 acting on A looks like that, but if we then focus on the forces in the rod itself, this means that there must be a force like that in the rod and a force like that in the rod, which means that the rod is in compression, because you can see these two T forces, these red T forces inside the rod are pushing in. So because of that, the rod is in compression or thrust. And just to really clarify this, these blue forces here and here are forces acting on the particles. These red forces are equal and opposite to these, but they act internally in the rod. We referenced this at the very start of this video, if you go back and have a look, that a rod is different to a string in that there will be there's the potential for a rod to be stretched and to be in tension, or to be pushed so that it is in compression. So now let's look at the final part of this question, which is where the 12,000 Newton braking force acts on B. Now, we've set up the three force diagrams again, the only difference being that the 12,000 Newtons acts on B rather than the locomotive. We're going to assume that the acceleration is to the right. We're going to take going to the right as positive. You'll see from the previous question that it actually doesn't matter, because if something turns out to be in an opposite direction, you'll get a different sign, and you just need to interpret that accordingly, as we did in the previous question. Now, the acceleration is going to be the same as it was in the previous question, because if you look at the system overall, there's nothing that has changed. The 12,000 Newton force, the 200 Newtons, the 200 Newtons and the 600 Newtons are all acting backwards, and the same forward forces are acting. So actually the acceleration will be no different to the value it has been previously. So that's equal to negative 0.18571. If you want to, you can verify this by setting up the three simultaneous equations and solving them for the acceleration, or you can treat the system as a whole and you will find you get the exact same acceleration. Now, we need to find the value of T2, so we're going to focus purely on particle B for this. We have F equals ma, again, and we have T2 forwards, minus 200 minus 12,000, which equals the mass of B, which was 10,000, multiplied by the acceleration, which we have up here. Don't worry about directions. Don't worry about whether you've got T2 in the right direction or not, because you can interpret your answer carefully at the end. So we can very simply from here calculate our value of T2, and it comes to 10,000, 342.857, etc. So we can round that to 10,343 newtons to the nearest whole newton. Now, this is positive. Note that. Which means that this diagram is correct, which means that the forces are marked in the correct position, which means that if we think about B and A and the tow bar that connects them, this force here in this situation is actually in the correct direction. This force on A is also in the correct direction. But if we look at the forces acting in the tow bar rather than the forces on the particle, then there must be an equal and opposite force in the tow bar like that to balance this T2, and an equal and opposite tow bar tension like that as well, which means that if you think about the tow bar, look at the T2 forces, the red forces, they are pulling apart. In the previous question, they were pushing in. So that tells us that the tow bar is in tension in this example. So just to reiterate this force acts on particle B, this force acts on particle A, these forces act within the tow bar and are equal and opposite, and because they're pulling outwards, they're pulling the tow bar, which means it is in tension, whereas in the previous question, the red forces in the tow bar were pushing inwards, which meant it was in compression.